Well, good morning, ladies and gentlemen. Mr. Dorfler back again for our last installment of Daily Dose of Dorfler for section 6.1. So, yesterday, or in the previous day's discussion, we talked about the impulse momentum theorem and how the impulse on an object can alter another object's momentum. I also mentioned that this concept is pretty useful when discussing how long or how far it takes for objects to stop, much like vehicles, which can lead into different engineering designs and so on and so forth down the line. So we're hopping right into today's practice problems. Again, we're utilizing the impulse momentum theorem, but you'll notice that quite a few of these questions you're going to have to include a hopefully familiar face to help us solve this, okay? So let's start off, and I'll get to that here in just a moment. You're definitely going to need your formula sheet for this because we're going to be calling back someone from the past. Anyway, we have a 2,240 kilogram car traveling to the west, slows down uniformly from 20 meters per second to 5 meters per second. How long does it take the car to decelerate if the force on the car is 8,410 newtons to the east? This is a two-part question. Okay. The second part is how far does the car travel during the acceleration? We're going to come back to that. Okay. That's our special little friend coming back to say hi. So we're going to take a peek at just the first part. We're going to figure out how long does it take the car to decelerate. Okay. So first thing is, let's start writing down some information. Okay. We know that the mass of the vehicle is 2,240 kilograms. We also know that the vehicle is initially going 20 meters per second to the west. But again, these are vector quantities. So west is going to give us some new signage. So since it was 20 meters per second to the west, it's going to have negative 20 meters per second. The final velocity, according to this problem, again, the car is still traveling west, and it doesn't quite stop all the way. It slows down uniformly to 5.0 meters per second west, or negative 5.0 meters per second. We know that a force of 8,410 newtons to the east was causing it to slow down at that rate. Okay, so the first thing is we're going to do right now is we're going to solve for our, delta t. We're also eventually, in our next question, we're going to solve for how far did it go. Okay, so we'll come back to that in a second. So again, going back to our impulse momentum theorem, the formula is F delta t is equal to mvf minus mvi. In this case, we are solving for t, so we need to rearrange this equation to solve for t. So we're going to get delta t is equal to mvf minus mvi all over the force. So now we simply just go ahead and plug in our values here. Again, our mass of 2,240 kilograms, our final negative 5.0 meters per second, minus, again, our mass of 2,240 kilogram, multiplied by our initial velocity of negative 20 meters per second, all over the force of 8,410 newtons. So again, you can pause the video right now if you want to, but I'm going to go ahead and solve for this, and you're going to get an answer of 4 seconds. All right, so we determined the time there. The next part was how far does the car travel during the acceleration? Here's a couple key things, okay? First of all, we are told that the vehicle slows down uniformly. Now remember, just because it's slowing down does not mean it's not accelerating, okay? So it's accelerating uniformly from 20 meters per second to 5 meters per second. So uniformly is a key word, okay? And we're assuming that's going in a straight line because we're not told otherwise. So we need to reach back all the way to chapter 2, and I believe it's section 2 of chapter 2, where we have the formula for displacement with uniform acceleration. Okay, so I'm going to write this down, and you can rewrite this down if you want to, or you can go back to chapter 2, section 2, highlight this. Either way, make a note somewhere. I don't care if you rewrite it or what have you. But the formula to solve for how far this car traveled during this slowdown period is going to be delta x is equal to 1/2 times vi plus vf times delta t. That's why it's important. We can't do this formula until we determine how long it took. Okay, so now we can go ahead and start solving for our displacement. So 1/2 times, excuse me, our initial was negative 20 meters per second plus our negative 5 meters per second multiplied by 4.0 seconds. So once we've got that set up, we can go ahead and enter that into our calculator. And again, you can pause the video if you want to, but you should get an answer of negative 50.0 meters, or more precisely, we have in our final answer, we got to remove that negative sign. And so we're going to have 50.0 meters to the west. So that's how we solve these types of problems. Let's do a couple more. While I'm erasing this, you're going to need to open your book up to page 203. And we're going to do a few of these once I locate them in my notebook. All right, let's look at number 2. Number 2. We're not going to do every part of number 2 here. But, excuse me, let's do 2A, okay? A 2,500 kilogram car traveling to the north is slowed down uniformly from an initial velocity of 20 meters per second by 6,250 Newton braking force acting opposite the car's motion. Use the impulse momentum theorem to answer the following question. What is the car's velocity after 2.50 seconds? Okay, so we're solving for something a little different here. So again, write down what we know. The mass of the vehicle is 2,500 kilograms. Okay. The initial velocity was 20 meters per second. And again, it's going north, so it's going to remain a positive value. The force is, again, the force is acting in the opposite direction of the motion. So if the vehicle was moving north, and the question even says that the force was in the exact opposite direction, so we have negative 6,250 newtons. And we're concerned about how what is the car's velocity after 2.50 seconds. And so we're trying to figure out our final velocity here. So again, taking our F delta T is equal to mvf minus mvi. Rearrange it to solve for vf. So we're going to have vf is equal to F delta T plus mvi all over m. So solving for this final velocity, again, putting in your numbers here, force is negative 6,250 newtons. Our time is 2.50 seconds, plus our mass of 2,500 kilograms times the initial velocity of 20.0 meters per second, all over 2,500 kilograms. So again, you can pause it. After you've calculated this, you should get an answer of 14 meters per second. And again, it's a vector quantity, it's velocity, so don't forget to add the direction. The car was traveling north, so we're going to stay with that. 14 meters per second north. So its initial velocity was 20 meters per second. After 2.5 seconds of these parameters, it will now be going 14 meters per second north. So that was 2A. Now let's look at number 3. Okay. Number 3 says, assume that the car in sample problem C has a mass of 3,250 kilograms. How much force would be, we're on 3A, how much force would be required to cause the same acceleration as in item 1? Use the impulse momentum theorem. Okay, well again, let's jot down what we know. The new mass we're going to be using is 3,250 kilograms. There's here on my marker. Again, the initial velocity is negative 20 meters per second because we're going back to the problem that was in our PowerPoint here. This time, the car is stopping. Oh, you know what? Sorry, I was like, wait a second. So in question number one that we did not do, it also is built off of the sample problem that we did, the first question that we did. But in that scenario, the car stopped. So it had a velocity of 0 meters per second, and that's what we're building off of. Sorry about that blunder, but so that's where the 0 came in. It came from question number 1. So where it came to a complete stop, that's why I put 0. So apologize for that. Anyway, back at it. Lost my spot. And also, if we were to have done question number 1, we would also have noticed that in this scenario, it took 5.33 seconds for the car to come to a complete stop. Okay, so, oops. I knew I should have done the first one. Anyway, we are here to solve for force, okay? So again, F delta T is equal to mvf minus mvi. I don't know why I did that. We need to solve for F. So F is going to equal mvf minus mvi all over delta T. Go ahead and plug in our values. Again, our mass is 3,250 kilograms. Its final velocity was 0 meters per second, minus the mass again, 3,250 kilograms, times negative 20 meters per second, all over 5.33 seconds. Go ahead and pause the video if you want to, but you should have 1.22 times 10 to the 4th newtons east when it's all said and done. So again, the reason why it's to the east is because in the original problem, the car was traveling west and the force must be acting in the opposite direction. So there you have it, a kind of rundown of all the types of questions that you're going to see for your problem bank. Now, speaking of problem bank, this is what I want you to do. This time I want you to circle the following questions. These will be the questions that you do complete for your homework. Circle number 1. Circle number 2. Circle number 3. Circle number 6. Circle number 7. Circle number 8. And circle number 9. Again, 1, 2, 3, 6, 7, 8, and 9. Yes, I probably could have had you cross out the ones that weren't mentioned, but this is more fun. So again, That's going to be your problem bank C. Okay. Don't forget that once the day after your this video, you're going to have a quiz over section 1, so make sure you are up to date. It's going to be on Google Forms. Fairly short quiz, so just keep an eye out for that. Keep an eye out for all due dates. Again, we are at a new semester now. Please be diligent on staying up with your homework. Again, if you have any questions, feel free to send me an email, a post in Classroom. But until then, I look forward to hearing from you, and have a great day.